Thanks for being here. I am very excited to be talking to you all about Unison. It is a new programming language with kind of special support for building distributed systems. This is joint work that I've been doing with my awesome colleagues Arya, who is in the audience here, yay, and also my other colleague Runar, who just had a baby, and a bunch of awesome open source contributors, and I'll flash up their names at the end of the talk. So what is Unison? So it is a open source, statically typed functional language, very much influenced by a few languages, Haskell, Erlang, and this research language that's very interesting called Frank. Unison itself has been sort of a research project for several years now, but I would say the past year or so we've really been focused on trying to turn it into something real that you could use for real stuff. And we are almost there. We are currently alpha testing our very first release, which is super exciting. It is a public alpha, and I'll say how you can participate in that if you're interested at the end of the talk. So what's sort of the motivation here? Like why another programming language? So, I mean, in general, just I love programming. I've been doing it for about 20 years, and I feel like the essence of it is so much fun. It's captivating. You know, I'm excited to go to work every day. But there's also many aspects of programming that are sort of not as fun, that feel like needlessly arcane or complicated. And really wanted to just kind of design a new language, really starting from first principles, being willing to rethink anything and everything about how programming currently works, and see if it was possible to create something better. And so that's sort of like overall kind of the guiding philosophy, I guess, behind Unison. But then there actually is one very specific core technical idea that the language is sort of based around. And I want to sort of share that idea and explain it clearly, and then show sort of all the benefits that we're getting from building on this idea in Unison. And it's kind of a simple idea. It's not really a new idea, although no one has really tried to build a programming language around this before. So these next two slides are like the most important slides of the talk, I think. So because we're going to be like building on them. But so what's the core idea? It's in Unison, we're going to identify definitions not by their name, but by a hash of their content. So if we define a function factorial of n is equal to the product of the numbers 1 through n, it actually doesn't matter whether we call that function factorial or whether we call it blah. It doesn't matter whether we call the parameter n or whether we call it z. It's the same function. And we can compute a content hash of the implementation of that function. And let's say that hash is whatever, J1E. Okay, in reality, these are going to be 512-bit SHA-3 hashes. Okay, but I'm not going to show those in the slides for obvious reasons. Okay. So, we say that the code is content addressed. It's identified by its content. And we're actually going to do something different when we store the code in a Unison code base. So rather than storing a Unison code base just as a collection of text files, where the text is just this completely unprocessed form of your program, right? So instead of that, what we're actually going to store is, for each hash, we're going to store its serialized abstract syntax tree. So a very processed form of the code that's sort of easy to manipulate and do things with. So this is not the exact Unison code base format, but this sort of gives you the basic idea. So we have a .unison directory, and then within that, we have a subdirectory, one for each hash. So our factorial function, we have a directory for that hash, and then within that directory we have this AST file, which is a serialized form of the factorial program. And then very important is that separately from the AST is we are storing the names, or the name of that definition. So the name is just sort of separately stored metadata. So we're saying this hash has the name factorial, and it also has the name blah, and maybe it has 50 other names too. And then we would have the same kind of structure for other definitions in a Unison code base. So what's actually in this serialized syntax tree? So if you look at the definition of factorial, it's actually it has 3 dependencies. It's referencing product, it's referencing the function range, and it's referencing the function plus. So what's actually stored in the syntax tree is not those names. It's actually the hashes of product, range, and plus. And then when we actually compute the Unison hash for factorial, we do some further normalization. So, we normalize what the names of local variables are before we compute the hash. So, okay, bottom line, these Unison hashes, unlike names, they uniquely identify the exact particular definition that we're interested in. So the hash of factorial, it uniquely identifies factorial, and it pins down the exact versions of all of its dependencies. So it's like an unambiguous way of referring to a particular piece of code. And so that's an idea that we're going to be building on. So I guess show of hands, are those 2 slides pretty clear? Raise your hand if that's clear. Okay, cool, great. All right, so that's it. That's the idea. That's Unison. Okay. All right, so okay, so it doesn't seem like much, right? But we're going to get all these benefits by building on this idea in Unison. So first sort of thing is we're going to get a really nice story for doing code base management. So we're not going to have builds anymore. We're going to be able to do renames trivially. We're going to be able to cache test results, so we don't have to keep running the same tests over and over. We're going to eliminate dependency conflicts as a thing. That won't be something we have to worry about anymore. We're going to get a nice story for having typed durable storage without any sort of boilerplate of writing JSON encoders and decoders. And then kind of the domain that was sort of a motivation for this design decision in the first place is we'll be able to have Unison programs that describe entire elastic distributed systems and which deploy themselves at runtime as they're executing onto thousands of nodes. That's okay. That's not done yet, but that's where we're going. Okay. Okay. So I'll make it clear what's actually implemented now versus what's in the pipeline. But okay, cool. So I'm basically going to spend the rest of this talk going through these benefits and seeing how they emerge from that one design decision of content address code. Let's look at renames first. This is kind of an easy one. So because we're storing the name separately from the syntax tree, it's really easy to just replace that name with something else. If we want to say rename factorial to transmogrify, we just say, okay, great, we'll get rid of that factorial file and add a transmogrify file, and boom. The function has been renamed. So very important is that, first of all, we are not behind the scenes doing a whole bunch of text manipulation on behalf of the user to make this happen. We really are just updating that name in one place, which is cool. But even better than that is that this doesn't actually break anyone's code, including our downstream library users who we may not even know about, right? So right now, if you publish a library and you decide you want to rename a function in that library, you're basically on your next release, you're going to break all your users' code, and that's really unfortunate. So because the AST is referring to things by hash, You can move things around, rename them, and it doesn't break anyone who's depending on your code, which is a really nice property. Okay, that's cool, right? I think that's cool. That was like, it's one of these things where if you're designing a system today and you ask, would you rather have that or would you rather have what we have now? It's sort of like, well, this is clearly an improvement. So it's just a nice, easy win that we're getting. Okay, so another thing is that we don't have builds anymore. So once we've added factorial to our code base, that definition never changes. It just is. And so we never need to parse or type check that definition ever again. And when we're writing, say, a test that is referencing factorial, we are just going to look up the type of factorial and just pass that to the type checker when we're just type checking just this one little snippet of code that we're actively editing. So generally, and I'll show during the demo, you're never really going to be waiting around for the compiler to process hundreds of text files just to parse and type check your code. And so the way we do that is we actually just also, alongside that hash, we store the AST, and then we also store what was the type of this definition. And then the type checker can just look that up and type check just the new code that we're writing. And then also very important is that this isn't just a sort of ephemeral state of your IDE that's doing some like incremental caching. It really is that as soon as anyone has written factorial and added it to the code base and shared it, no one else in the world who obtains that definition needs to parse or type check factorial either, because it is part of the Unison code base format. Okay. Another thing we can do is we can actually cache test results. So Unison is a functional language. It doesn't just allow sort of unrestricted side effects. And so, and unit tests do not have access to I/O. Of course, you could write integration tests that do I/O, but unit tests don't have access to I/O, and so they are by definition going to be deterministic. They're always going to yield the same results. So if factorial 5 equals 120 now, it's going to continue to equal 120, forevermore. And so we can just cache that test result. And the way we do that is just associated with the hash, we might keep the AST, the type, and hey, what was the result of evaluating this hash? Okay, so we're getting all these nice properties, and it's really because of this general idea that the code base is append-only. So so nothing is ever changing. We're never modifying or mutating a definition. We're only ever introducing new definitions. And because nothing is mutating, we can cache all sorts of auxiliary information and associate it with these hashes. And we don't need to worry about sort of complex cache invalidation logic like what your IDE has to do to kind of maintain a compilation cache while these text files are being mutated out from under it all the time, which is super complicated. So we kind of are sidestepping a lot of that complexity. Okay, so now for the scary part, I'm actually going to try to give a demo of this. And but first of all, like discovering those 6 slides or whatever worth of information was just like a completely mind-blowing experience. Just to see all these things just sort of emerge, and it's been really cool. It's been a really cool project to work on as a result. So all right, let's move to a demo here. How am I doing on time? Okay. So I have here, on the right-hand side, I have, and is that pretty legible, the font? Is that big enough? A little bigger? Darker?
Light on the left side.
Light on the left side? Mm-hmm. Like that? right, I'll try just bigger. Sorry. All right. Okay, so on the right-hand side here, I have the Unison tool. And we call this the Unison Codebase Manager. It's the thing, it's sort of this all-in-one tool for running Unison code, working with the Unison codebase, you know, renaming things, doing refactorings, parsing, type checking code. And then on the left-hand side, I just have my favorite text editor, Vim. You can use whatever text editor you want. And I guess I'll sort of show a few things here. So one of the things so the code base is in this nicely processed form where we know the type of everything and it's very structured. And so we have, you know, a lot of interesting, like useful things that we can do. So if I want to just do a search for some definition, I might, you know, say list, tab complete, and then, so you can sort of search for definitions this way, look them up by type. I could even do a type-based search, find me definitions that have this type, that take a natural number and a list and return a list, and it tells me, okay, there's actually two functions, take and drop. So we can build up all these like indices on the code and just sort of maintain that in a very straightforward way, which is cool. So another thing that that Unison is doing is it's actually watching for changes to these .u files in the current directory. And we call these scratch files because they're just kind of places where you scribble down some code, and once you get it working, you add it to the code base, and then maybe even just delete the scratch file because now the data is in the code base and it's all good. So if I save the file, it sort of picks that up right away and says, okay, there's nothing there, but let's go ahead and, you know, add a definition, and it'll parse and type check the file. Anything below these triple dashes is, we call that the fold. It's going to just be ignored. It's like commented out. So any line that starts with this greater than, we call that a watch expression. It's going to be evaluated on every file save. So you notice like sometimes that arrow is red, and then if I save it again, it is now gray. So Unison will actually cache those watch expressions, so you know, they're not going to be reevaluated every time. So it's like, you should never feel like, oh, I can't save the file because it's going to redo this huge computation. It's just going to sort of cache it based on that hash. Okay, so these watch expressions are kind of replace traditional like read eval print loop. You just kind of like write code and then interactively evaluate different expressions. So let's go ahead and define factorial, and I'll give a couple test cases too. So first I'll define product. It's by folding the numbers, starting with 1, multiplying them together. And I might check, okay, product, that seems to be doing what I expect. And like, so once I'm happy with the definition, notice this message. These new definitions are okay to add. So I'm going to type the add command, and it says, okay, I've added these definitions. So now the syntax tree of product is in the code base. And I could view it, and I can, all these commands have tab completion, so that's kind of helpful. View it, and it'll render that syntax tree with import statements inserted, you know, the most sort of accurate, precise import statements. So you can be kind of sloppy about your imports, because that's not actually part of your, that's not actually part of what's stored in the code base. So one thing, and then once it's in the code base, I might just, I don't know, just delete it. It's still there. I could get it back if I wanted to get that back, like basically dump it back to the scratch file, so I could look at it or make changes to it. You know, I can type that edit command, but you know, I'm happy that it's there, so I'm just going to leave it there. One thing I was going to point out is, okay, if we look at product, it uses this function foldL, and if we wanted to rename foldL to, I don't know, frobnicate, and then we view product again, you can see it picks up that new name for foldL. Okay, but I kind of like the name foldL better, so I'm just going to undo that. And it shows me the diff of, you know, what was just undone. You can also view the history of, you know, explore the changes you've made. There, it's very semantic, it's sort of not showing these textual diffs, it's showing like, okay, this definition was changed or this thing was renamed. Okay, cool, so let's define factorial. And yep, it's the product of the numbers 1 through n. And I'm gonna just define some tests, also using watch expressions. These are called test watch expressions. They start with tests instead of just a single greater than. And I just have a few examples here, which I save the file, everything type checks. You can see the tests pass, and they're actually cached. Why are they cached? It's because I ran through this example earlier. So they just happen to already be in the test cache. And once I'm sort of happy with this, I can add factorial and its tests to the code base. And I'll go ahead and just even delete those definitions. Now, if I run the tests, it's not actually running anything. It's just looking up those already computed test results in the cache. And even if I rename the function that's being tested, like I rename factorial to blah, and I run the tests again, it's still just not actually doing anything because the test cache is keyed by the Unison hash. So renaming doesn't affect any of that caching. Cool. And then I guess one last example that I was going to show is, later in the talk, I'm going to show like a really simple distributed merge sort implementation. And I just wanted to show that rather than like switching back and forth again. It's a distributed sort, merge sort function, and I'm just running it locally, sort of simulating execution locally. And I'll show the actual source code for this on a slide later. But anyway, so this is kind of the basic sort of environment. It's kind of low tech, you know, you have your text editor, you've got Unison running, and you know, you just sort of write code, it's very interactive, and it's nice. All right, cool. So, what are some other benefits of this idea of content address code? So I said that we're gonna eliminate dependency conflicts. So dependency conflicts, they arise when you have, generally when you have diamonds in the dependency graph. So suppose, I'll explain what that means. Okay, so we have Alice, she's written a library, has some definitions in it, has an employee type, it has some functions in it, and Bob and Carol are making use of that library. Maybe Bob works in HR, and so he needs access to the employee type, and maybe Carol works in accounting, and she also needs access to some of the definitions for running reports or whatever. And then Dave wants to make use of Bob and Carol's libraries. So this is a diamond dependency, because shaped like a diamond, okay. So this by itself is not a problem. The diamond dependency problem, is when Carol and Bob may have different ideas about which version of Alice's library they want to use. And maybe Carol wants to use Alice version 2 because it has some new functionality, and Bob still wants to use version 1. And in a real programming language ecosystem, you know, these situations can be very common, and it, you know, can result in all kinds of problems. And it's like, oh my gosh, we have a dependency conflict. Like, what do we do? Everybody stop what you're doing. Like, we need to like resolve the situation and get everybody to agree on like which version of Alice's library we're going to use globally across this entire code base. Okay, let's breathe. Take a step back. Okay, what are these so-called conflicts really? Like what are they really about? So I would say they are caused by the fact that all of our libraries have to occupy a single shared namespace where you cannot have multiple definitions sharing the same name. So like for basically artificial reasons, you can't have Alice version 1's notion of employee in the same code base conveniently with Alice version 2's notion of employee, because they're the same type because they're named the same thing. Except they're not the same type. They're different types. And if we just had a reliable way of consistently referring to types, like say a hash, a content hash, then it would be perfectly fine to allow as many different versions of the same library in our code base. And basically there's no issue. So that's what Unison does. And it's, I guess, to give like maybe some intuition for like how this is not a problem, it's sort of similar to, suppose you had two email types floating around in your code base, and they have different fully qualified names. That might be totally fine if those two email types are being used in like different parts of your code base. It's like no big deal. Maybe if those two email types are like coming together in the same piece of code, you may have to write a regular function to convert from one to the other. Maybe you would decide like, hey, let's kind of standardize on an email type because we're like using it all over the place, and like it'd be easier to just have one. But the point is that it's not really a conflict, it's just sort of like a thing that you may choose to do something about. And it's definitely not something that prevents you from getting work done, like what might occur if you suddenly have a dependency conflict in some of the libraries that you're trying to work with. Okay, cool. So easy typed durable storage. This one's kind of near and dear to my heart. Okay, you're writing some code. You've got some data. You want to save that data and read it back later. Maybe it's a list of employees, okay. And so what do we do right now? It's like list of employee. That's like this nice typed, structured thing that you can compute with. And what do? We're like, okay, throw all that out. We're gonna just like dump it to just a blob of bytes or JSON, throw out all that type information. Oh yeah, and we're gonna make you write a bunch of boilerplate to actually make that happen. And like, okay, why do we do that? Well, it's partially for a good reason. So we wanna be assured that when we go to read that information back later, we wanna be assured that it has like a well-defined format that we'll be able to get back something that contains the same information about what was in the original list of employee. So, we may be, the notion of like what an employee is may have changed between the time we wrote it out and the time we're reading it in. And so we're like, because the notion of an employee may have changed, we need to sort of write all this manual code and do all this stuff. Okay, but this is really the same kind of problem as the diamond dependency problem. If we simply don't if we don't refer to things by name, if we say that what an employee is simply like the hash of that type, that can never change. So it may be that the name employee is assigned to a different type in version 2, but we can always still deserialize the version 1 notion of what an employee was without any problem. And it's perfectly fine to have multiple versions of what an employee is floating around your code, kind of for the same reasons I already talked about. So this gives us like a really nice story for like defining like reliable, durable data structures. You can just very straightforwardly, hey, I want to make this persistent, and then I want to be able to unpersist it later. And you can do all kinds of neat stuff with that. Okay, So last one here. So let's talk about distributed systems now. The basic idea, we'll look at an example here, just conceptual before I actually show any Unison code. Suppose Alice wants Bob to, so Alice and Bob are two nodes in a distributed system, and Alice wants Bob to compute something. Bob, go compute factorial of 7. Okay, so except in Unison, Alice is not going to send the name factorial over to Bob. She's going to send the hash of factorial over to Bob. And Bob may say, and that hash uniquely identifies what function is being evaluated. And so Bob might say like, oh, actually, I don't know about that hash yet. Can you send it to me? And Alice says, sure, here it is. And then Bob says, great, I've got everything I need. I'm going to go ahead and run that. And then Alice, here's that result. Boom. And Alice keeps going. So this idea of having a content or having a reliable identifier that always means the same thing on all the nodes in your system, that hash, that sort of gives us this nice, efficient, dynamic deployment protocol. And sort of more generally, it's like if you know about Merkle trees, it's sort of like a Merkle. If you take the dependency graph, it's sort of like a Merkle tree dynamic sync operation, and it can be made very efficient, very straightforward. Okay, so this also works. So Alice and Bob don't need to be like named, nodes that you've like set up in advance either. So it could be that like Alice just conjures up a node from the cloud or from this, maybe it's a cluster of nodes that you're managing. But the point is like you haven't set up that node in advance to have any code. Like you didn't have to like, set up its class path and make sure it had all the right jars, blah, blah, blah. It's like it can just sort of start out as this empty Unison node that doesn't really know about any definitions. And simply when you first contact it, it may do some dynamic syncing of code that's needed. And of course, it can be cached for next time. And so this sort of works for defining elastic systems where you're really just provisioning these more anonymous compute resources and then kind of just discarding them when you're done. Cool, so let's look at actually some Unison code for how this plays out. I'm defining a function here, factorial at, takes in a node Bob. I'm going to say at Bob, go ahead and start computing factorial of 7. The quote here is saying, basically, don't evaluate factorial of 7 here. Delay that and ship the unevaluated thing over to Bob so he can start evaluating that. This returns like a future. So at this point in the code, factorial of 7 is running on the Bob node. Here I'm saying at spawn, at a newly conjured up compute resource, start computing factorial of 8 in parallel, and then maybe I'm going to wait for those two parallel computations to complete and then add them together. This is a really silly example, I admit. All right. Let's look at the type too, because this is kind of important. It's, so you see these funny curly braces attached to the arrow. So in order to get access to the at, spawn, and force operations, we need to tell Unison that in the types, we need to say that, hey, we're okay with remote stuff happening in this definition. And if we were to like delete the remote from here, Unison would complain. It would say like, hey, you're trying to do something that requires the remote ability, and your types don't give you access to that here. So we still have nice types to kind of keep track of things and like prevent you from getting mixed up about when when things are happening that you want to keep track of. Here's like a little bit, this is the distributed, sort of a toy distributed merge sort implementation. Looks a lot like a regular in-memory merge sort. You're dividing the list in half. You're recursively sorting both halves, and then you're merging the results. The only sort of difference is that we are, the recursive sort call, we're doing that in parallel on two different newly provisioned compute resources. Okay, so this interface to distributed programs is like, this seems like the dream. I mean, there's no JSON, there's no opening network. So it's just like, you just wrote code and you just kind of annotated where you wanted concurrency and distributed execution to occur, and then, what is it, just magic? Like, what's going on here? Okay, so we're working on this right now, but the idea is that distributed programming should just be a library. So we don't think that we are going to have all the answers about what is the right abstractions for building distributed systems. And so remote is just, anyone can define these, we call them abilities, where you just define a set of operations, the at, force, and spawn. And then with regular Unison library code, you can define different interpreters that handle these operations. So one of the things you might do is have one interpreter for these operations, which just runs everything locally. Maybe it even simulates failures and injects latency, things like that. But then you could also have another interpreter of this ability that attached the computation to an actual source of elastic compute and actually was running it for real in parallel on lots of nodes. And the idea is like, you should be able to write these libraries just as well as we can. And it's really the only things that the Unison language needs to provide are some of those primitives for doing like the serialization of computations and syncing and things like that. And then you could sort of build up your own protocols and abstractions. And I'm like super excited to do that, and also to see like what other people will come up with, and very, very exciting. So I just want to say that the things that I showed here, just this really simple remote ability is really, this is more for just like batch computing. So it's like, you essentially have a pure program, like it's something that in principle you could run just as a regular purely functional program just on your one computer. It's just you're saying like, hey, it would be nice if my laptop were actually a supercomputer and I could just have access to as much compute as I wanted. So that's certainly a useful thing, for doing things like data science, machine learning. Lots of things are just batch computing. But I think the other really interesting use case in distributed systems is when you have these more stateful elastic services where you have lots of concurrency, and but then the system is sort of coming to some consensus or agreement about what the state of the system is. So this would be something like you're implementing some sort of key value store, and it's massively parallel, tons of updates happening concurrently on all these different nodes, and like it would be great if you could write services for that kind of thing in Unison as well. And so this is sort of a topic of ongoing research. There's a lot of interesting research that's like happening in the distributed systems and functional programming communities. That's sort of, we really want something that's nice, like that's as nice as that sort of batch computing thing where like, so yeah, just trying to, this is active area of research, and I think it's super exciting. And yeah, I'd say in the next 6 months or so, we'll start to see more about kind of what that API could look like. So yeah, that is the end of my talk, so let me just say a few things. First of all, thank you. I will also want to say thanks to just all the open source contributors who have contributed to Unison and helped get it to this point. If you're interested in helping out with alpha testing, if you go to unisonweb.org and you'll just follow the links there, it'll sort of guide you to the doc site and then tell you about how you can get started. And then other thing is we're having just an informal get-together at the Sliced Pint at 6 p.m. after the conference ends today, and feel free to come by and say hello and have some pizza or drinks, and any last-minute coordination we'll do in the #Unison channel on the Strange Loop Slack. So I think that's it. All right. Thank you.